Hi friends, this is the 12th lecture in the lecture series for the preparation of GATE in Mechanical Engineering, and this is a star lecture in which we will be providing you the capsule of entire concepts of conduction, that is both the steady and unsteady heat conduction. Along with we will be providing you the capsule of fins. Okay, so let's move on. So the conduction is a heat transfer phenomena which is occurring in a stationary medium which is having some temperature gradient. That is, if T1 is greater than T2, then some heat will transfer from T1 to T2 like this. Okay, and this heat transfer rate, which is given by the equation Q dot by A, which is equal to minus K dt by dx, and this equation is nothing but the Fourier's law of heat conduction. Fourier's law of heat conduction. Okay, and see, and in this equation we are having a term called Q dot by A, and this is called the heat flux, which is given by the or denoted by Q bar, and this is one dimensional in nature. So the general form of Fourier's law is Q bar is equal to minus K delta T, where this delta T is the temperature gradient and K is the thermal conductivity, Q bar is the heat flux. Okay, and then the general form of heat conduction. General form of heat conduction. This general form of heat conduction is nothing but an energy balance which is done on a body in which some heat transfer is occurring by conduction, and the equation will be del dot K delta T plus Q dot G will be equal to 1 by, not 1 by alpha, it's rho C dot T by dot T. So this equation is the general heat conduction equation, and if we are provided with some isotropic material in which the thermal conductivity is constant in every direction, we can write the general form of heat conduction equation as del square T plus Q dot G by K will be equal to 1 by alpha dot T by dot T, and this equation is called the Fourier-Biot equation. Fourier-Biot equation, and this equation is having some special cases, and the first special case is for steady state heat conduction, that is dot T by dot T equal to 0, and with heat generation, that is Q dot G not equal to 0. This Fourier-Biot equation can be written as del square T plus Q dot G by K will be equal to 0, and this equation is called the Poisson's equation. Okay, and the second special case is nothing but for unsteady state heat condition, that is dot T by dot T not equal to 0, and with no heat generation, it is Q dot J is equal to 0. We can express the Fourier-Biot equation as del square T is equal to 1 by alpha dot T by dot T, and this equation is called the diffusion equation. And the last type is, or the third special case is for steady state heat conduction, that is dot T by dot T equal to 0 and no heat generation, that is Q dot G equal to 0. We can rewrite the Fourier-Biot equation as del square T is equal to 0, and this equation is called the famous Laplace equation. So that's all about the general concepts that are present in this conduction analysis. Okay, and then now let's deal with the steady state heat conduction. And for this steady state heat conduction, we have dealt with one dimensional steady state heat conduction with no heat generation, that is Q dot G equal to 0, and the governing equation for this particular case was del square T equal to 0, and which is the Laplace equation, and this was the governing equation. And for this case we have considered this one dimensional steady state heat conduction for some geometries, and we have determined some heat transfer rate formulas and the temperature distribution formulas, and then some thermal resistance formulas and all. So this I will tabulate. First column we will be having geometry, then we are having temperature distribution, and then we are having the thermal resistance RTH. The first geometry was plane wall, and for the plane wall temperature distribution was given by H by L, which is a linear in nature, which is linear temperature distribution, and we are having the thermal resistance as L by K. And next, or the next geometry we dealt was hollow cylinder, and for hollow cylinder the temperature distribution was given by ln r minus ln r1 by ln r2 minus ln r1, and the thermal resistance was given by the equation ln r2 minus ln r1 by 2 pi kl. And see, the temperature distribution was logarithmic in nature, and then the last geometry we dealt with hollow sphere, and for this hollow sphere we are having the temperature distribution as 1 by r minus 1 by r1 by 1 by r2 minus 1 by r1, and that thermal resistance was given by the equation r2 minus r1 by 4 pi k r1 r2. So these are the geometries that we dealt in this one dimensional steady state heat conduction, and just memorize this table and we can calculate the heat transfer rate by the equation. Q dot is equal to delta T by RTH, and if we are calculating the Q dot like this, and then we can calculate the Q bar as Q dot by AC, where AC is the heat transfer area. Okay, so that's we dealt in the one dimensional steady state heat conduction, and then we dealt with the composite objects. And these composite objects are nothing but the plane walls or hollow cylinders or hollow spheres, and which are connected either in series or parallel combination. And for this type of composite objects we have to follow certain steps to analyze them, or to analyze the heat transfer. And the steps are, the first step is to determine the resistance of individual elements, and then the second step was draw thermal circuit and determine the equivalent thermal resistance. And this equivalent thermal resistance can be determined by using the formulas for series. We can use RTH equivalent is equal to R1 plus R2 plus etc plus Rn, and for parallel case we are having the equation of 1 by RTH equivalent is equal to 1 by R1 plus 1 by R2 plus etc plus 1 by R. So we can use these equations to determine the RTH equivalent. And the last step was to determine the heat transfer rate by the equation delta T overall by RTH equivalent. So this is the equation that can be used to determine the heat transfer rate. In sometimes we can write the heat transfer rate as UA delta T overall. And if we compare this equation with the above equation, we can find that this UA is equal to 1 by RTH equivalent, and the U in this particular term is called the overall heat transfer coefficient. Okay, and also for convective boundaries we are having this heat transfer rate or the thermal resistance RTH given by the equation 1 by H into A. Okay, where H is the convective heat transfer rate and A is the surface area over which the heat transfer by convection is occurring. And then in the steady state heat condition we dealt with the critical radius of insulation. Critical radius of insulation. Okay, and this critical radius of insulation is R, at which the RTH equivalent is minimum, and also the heat transfer rate is maximum. So that particular radius is called the R star, or the critical radius of insulation. At R equal to R star for cylinder, we can calculate the R star by K insulation by HO for cylinder, and for spheres we can calculate this R star as 2K insulation by H. These are for spheres. Okay, and if you are providing insulation, if we provide insulation to reduce heat loss, then we are having two possibilities, that is either the radius of insulation, that is R, greater than RO, that is radius of the pipe, or radius of the insulation is less than R of the pipe. In this particular case, keep the radius of insulation greater than the R plus value. Here any R value is enough, or it will do the job very well. In this particular case, we are having the heat transfer curve, or the heat transfer graph like this, that is, this is Q dot and this is R, and this is RO, which is the radius of the pipe, and this is the R star, which is the critical radius of insulation, and this is the radius which is determined by the equating the heat transfer rate with insulation and heat transfer rate without insulation conditions, and we can determine this particular R plus value. Okay, so that's it. And if we want to enhance heat loss, then we have to keep R value equal to R plus. So that's all about the steady state heat conversion. And then in the unsteady state heat conduction, what we dealt with, and we considered this unsteady heat conduction problems, or we analyzed by using certain method called lumped capacity method, and unsteady state problem will be treated as lumped capacity method only under two assumptions. That is, the first assumption is temperature should be uniform, that is, temperature is varying with respect to time, that is, temperature should be constant or uniform all over the body at a particular time instant, and also Biot number should be less than 0.1, and this Biot number which is given by the equation, or which is given as the ratio of R conversion by R conversion, and for a plane wall we can write this as L by Ka by 1 by Ha, and this will be Biot number is equal to HL by K, and if Biot number less than 0.1, this R conduction value will be minimum, implies the temperature is uniform. So that's why we have to consider the Biot number less than 0.1, and at the same time some other dimensionless number will come into existence, that is Fourier number, which is given as the ability to conduct energy to ability to store energy, and it is given by the equation alpha T by L square. Okay, and then we are having the lumped capacity analysis, equation, and it is given by theta by theta 0 is equal to T minus T infinity by T0 minus T infinity is equal to e raised to minus HAS by rho CV into T, and this particular equation is having certain different forms, and this can be also written as e raised to minus Biot number into Fourier number, and also it can be written as e raised to minus t by tau. This is tau, and this tau is nothing but the thermal time constant. It is given as tau is equal to rho Cv by Hs, and this tau will also be equal to C thermal into R convection. And the peculiarity of this tau is, if we are keeping the tau very minimum, then the temperature of the body will reaches the temperature of surrounding very quickly. So that is the peculiarity of this tau. And then we have dealt with the equation for the total heat transfer rate that is occurring on this particular body in which limited capacity analysis is doing, and which is given by the equation Q is equal to rho Cv into T0 minus T infinity into 1 minus e raised to minus Tf by tau, and this Tf is the final time. Okay, and then in the unsteady state heat connection we have dealt with the fins, and these fins are nothing but the extended surfaces which are used to increase the convection heat transfer by increasing the surface area, which is nothing but increasing the or which are nothing but embedding some kind of extra material to the body in which convection heat transfer rate is occurring. And the general fin equation, in general fin equation is given by d square t by dx square plus 1 by ac dac by dx into dt by dx minus h by kac into das by dx into t minus t infinity equal to 0. And for constant cross sectional area fin, we are having dac by dx equal to 0 and das by dx equal to perimeter p. So we can write the above equation as d square theta by dx square minus m square theta equal to 0, and the solution will be given as a e raised to mx plus b e raised to minus mx, and the solution can be determined from the boundary conditions. That is, there are two boundary conditions. That is, the first one is the base condition, and the second one is the tip conditions. And we are having at base the temperature T is equal to Tb and theta is equal to theta b, which is equal to Tb minus T infinity. On the tip conditions, there are three types of tip condition that we have considered, and the first is infinitely long fin. And for that case we are having T is equal to T infinity at x equal to L, and theta is equal to 0 at x equal to L. And the next was insulated tip. For that case, at x equal to L, we are having dt by dx equal to 0 implies d theta by dx equal to 0. And the last tip condition was convective tip. And for this convective tip at x equal to L, we are having it's minus k d theta by dx is equal to h into d theta. So these are the two boundary conditions that we are applying to determine the general solution. Okay, and let's tabulate under fins, that is the heat transfer rate, the effectiveness and efficiency of the fins of various tip conditions. So let's tabulate them. Okay, and here let's discuss the heat transfer rate, which is given by the letter q dot. And here we are discussing the infinitely long fin. Here we are discussing insulated tip fin. Here we are discussing the convective tip fin. convective tip fin. Okay, and here the q dot is given by the equation m into theta b, where m is equal to root of hp KC, and here the q dot is m theta b into tan h ml, where this m is root of hp KC, and this smaller term is smaller term which is given by the equation sp by KC, and the convective tip we are having q dot is equal to m into theta b into tan h m into LC, and LC is the corrected length which is given as L plus AC by P, and for uh, circular cross section we are having LC is equal to L plus D by 4, and for rectangular cross section we are having LC is equal to L plus T by 2. So that's all about the heat transfer rate, and then now let's discuss the effectiveness, that is epsilon, and this epsilon is nothing but the heat transfer rate with the fin to the heat transfer rate without fin, and for infinitely long fin this effectiveness is given by the equation hp by KIC, and for insulated tip condition we are having the effectiveness as hp into KIC into tan h ml, and see the effectiveness is proportional to P by AC, and is also proportional to K, and is also proportional to 1 by H. Okay, and that's all about the effectiveness, and then let's discuss the efficiency. This efficiency is given by the equation Q dot actual divided by Q dot ideal, and this ideal heat transfer rate is the heat transfer rate of the fin in which the temperature of the ender fin is uniform or constant. For that case, the efficiency of infinitely long fin is given by the equation 1 by m into L, where m is equal to root of hp into KAC, and the efficiency of insulated tip condition is given by the equation tan h ml by ml. So that's it. Thank you.